Well, looks like it's about time. Welcome back, everyone. Oh, it is time, in fact. Welcome back, everyone. We've all made it to the very last class. It's kind of hard to get here sometimes. Any questions at all before we get started? Okay, well, it's been just about a full 15 weeks. It's supposed to be a 16-week semester, but feels like just 15 because we'll be doing a take-home final exam. That means this is really our last in-person meeting, our last meeting over Zoom. But as you're working on this final exam, you're always welcome to send questions. There might be stuff I can't answer if it's a question directly related to the exam content. But if it's a question about, say, problems with RStudio, it can be a bit of a beast sometimes. Anything along those lines, I'm always very happy to help out. And you know what? If you're just stuck, it never hurts to just ask. I might not be able to give very many hints, but talking about why you're stuck in an email, just the action of talking about it, whether you're typing it out or in coding, they sometimes call it rubber ducky debugging, where you're literally talking to a rubber ducky. That process does help you solve the problem because your subconscious is working on it as you describe what you're trying to work on. So don't hesitate to reach out even on the final exam. I'll be happy to help out where I can. So what we're doing today, we're just going to do as many review problems as possible. We're not done with problem one. I was scrolling through there and my little reminder actually helped me not skip this one. So we'll finish off that problem number one. I also want to directly jump into a problem here on the chi-square test, since, we've solved two of them. We haven't done a homework assignment on that section, so I'm going to want to solve the one right after. It just makes sense for the sake of a review. After that, it'll be pretty much up to us, whichever review problem you'd like to take a look at, either from here or the other documents. If we don't have any specific ideas on which one you want to do, we can just go down the line on the problems we see. At a point at which it makes sense, maybe around 6:35, we will end the review and then just turn over to unlooking the exam and taking any last final questions. This one's going to look a lot like exam two that got converted to a take-home exam, so we kind of already know what to expect. It's 6 questions long, same kind of questions like you see in this document, but they have been randomized. So the larger thing that you're doing on this final exam is mainly choosing the appropriate statistical method. That's where a lot of the partial credit is going to come from. If you make some mistakes here or there, I'm not as worried as I am about choosing the right method. That's going to be the major takeaway on this final exam. Any questions at the moment so far, folks? Okay, well, let's see. I do have one last thing I want to say. We probably won't be able to solve every single problem on here. They are sometimes long problems. And after we're done with class today, around Friday, I'm going to start grading your assignment 10. I think that's the very first thing that's going to help you with the final exam, just getting your feedback back from that assignment. After I'm done grading all of your assignment 10s, I'll immediately work on solving whatever problems we didn't finish off here. So that's going to be my workflow over the weekend. I think that's all I have to say so far. Any questions at the moment, folks? Okay, well, let's get started. We are on problem number one still, but we nearly got through it. We did like all the mathy parts of this. But I did want to change one thing I did say on this document. We chose the method by looking at the variables, and we said that there's one quantitative variable, vascular health, another variable which is categorical, and its whole purpose was to determine which of the participants had the good chocolate, high in flavonoids, and which ones had the control group, the chocolate, low in flavonoids. I don't think that's a wrong approach. That's a great way to think about it. That is a true categorical variable. But the one thing I've looked at here on choosing the statistical method was I described how to choose this method slightly differently. I said if you're using the two sample t methods, you should have two independent quantitative variables. Let's bring that a little bit more in line. So back here, I want to make it's hard to say, not quite a correction, but in addition to this, let's think of this as really two quantitative variables. We can say one is vascular health with the good chocolate, as they did call it somewhere in there. And the other variable would be vascular health, and this was the control. This was the group that had the not as good chocolate. And let me put a box here, since the way we wrote our document was looking for two independent quantitative variables. They are independent because these participants, the 11 here and the 10 there, they weren't used twice. They only got used in the study one time. So think in these kinds of terms, and it'll be a little bit more in line with just how we describe this document. We could have said one quantitative variable and a categorical variable with two outcomes, but it just so happened we described it this way. So I want to put that addition here on the notes as well. Sorry for the confusion on that one. Does that make sense about the change we put in there? Okay, I feel like that's going to be a nasty thing that we didn't say right here. It could make choosing the statistical method along this list a little bit confusing on the real final exam. So coming down, what do? We said mu1, mu2 is going to be the true mean vascular health for participants given the flavonoid-rich chocolate and the low flavonoid chocolate. That's the control group. We're estimating a confidence interval, the difference in the parameters at 99% confidence. And to do all that, we had to grab the summary statistics and carefully crank out standard error, degrees of freedom, and finally our critical number. After doing all that, we're finally at this step. Our confidence interval goes x bar 1 minus x bar 2. Add and subtract the critical number t star multiplied by the standard error of the difference in means, x bar 1 minus x bar 2. Okay, let me see if I still have that screenshot. Oh, there they are. Here's our statistics. So now we're just dropping in 1.3 minus negative 0.96. This one's negative, indicating that it looks like their vascular health decreased. I'm not sure what was in that chocolate, but that's kind of strange. But I don't know what the units are either, so I can't tell if this is meaningful or not, really. I just know it's a negative quantity. So add and subtract the number that we very painstakingly came up with, 2.8843. Multiplying standard error, oh, and it's way up here. We've got it at 0.8596. The next step is just to jam all this into the calculator. Standard thing we usually did on the confidence intervals that you don't have to do. It's really up to you and the style that you write these out. But I think it's always helpful, especially if you're learning this content, to remind yourself what you're really doing at this stage. It's going back to these things, mu1 and mu2, and you're finally ready to give an estimate on that difference. These were unknown quantities, but we want to get a handle on them. All we need now is a calculator to make that happen. Any questions at all, folks? I'm getting to that stage of the method. Okay, so careful computing will give us, let's see, 1.3, that's really a plus 0.96, then minus 2.8843 times 0.8596. So here is the lower bound. Flip that to plus, and now we've got an upper bound. Just to save some time, let me take a screenshot so you don't have to watch me try to remember 4 or 5 digits. We're usually pretty bad at that. So we've got on our lower end a negative 0.22 if we round to 2 places. On the upper end, we have 4.74. Some measure of vascular health. Again, we're not entirely sure what those units represent here, but at least we've got it. So here's our full interval. Let me see if I can erase that since we no longer need it. We're done with the statistics, so we can eliminate that as well. All we need to do is give a conclusion. And if you like, you can add mu2 to all 3 sides of this integral just to make the interpretation a little bit more streamlined. So I'll go mu2, recall that's the control group, minus 0.22 is less than mu1, which is less than mu2, plus 4.74. Now, if this was a hypothesis test, and we did that test at a 1% significance level to match our 99% confidence, and it was a two-tailed test, we already see that there is no statistical significance here. It goes from a negative end to a positive end. So in other words, it's potentially true that the difference is zero. There's no effect at all in the population. But we're still going to interpret the confidence interval just as we see it, which means we need to grab this stuff here. On your real final exam, I did put in the structure of state, plan, solve, and now we're on conclude because it's kind of annoying to have to write in ourselves. I've been learning here. So you will have that extra skeleton of the problem. So here's the conclusion phase, where we want to look up our parameters as needed. So let's see, mu1 is the true mean measure of vascular health for participants given mu1 is flavonoid and mu2 would be low flavonoid. So now let's say, and just to make sure I don't forget, let's start with our confidence level. We're at 99% for this problem. So with 99% confidence, the true mean, or you could say average here if you'd like, vascular health for participants given flavonoid-rich chocolate, I'll just say flavonoid chocolate like we indicated there, okay, so we mentioned essentially just mu1, and now we can say is from or is between, any kind of fluff word you'd like to throw in there to connect the dots. I'll go with is from 0.22 lower. Notice I'm just putting in the positive 0.22 because we've already indicated the direction by saying lower. Up to 4.74 higher than, now we just mentioned mu2. Let's say the participants given low flavonoid chocolate. So that pretty much did it. That's our conclusion on this problem. One thing that people have done in some of their problems, which I think is excellent, is if you read a little bit further on, there could have been a larger question. Let's see here. A study examines the chocolate's effect on blood vessels function in healthy people. Let's see, I don't really see a big overall question, but you might have said, just to summarize everything you just did, it appears that there is no statistically significant effect going on in the population because of it going from the lower end to a higher end, potentially including zero. That wasn't directly asked, so anything extra you put in here is fluff, but make sure you do directly conclude on the confidence interval. So say what you see here, and same if it was a hypothesis test, whether you're rejecting or accepting whether you're rejecting your null hypothesis or failing to reject it. Well, any last questions, folks, on that problem here? Regan says, I'm unable to stay for the full class. No worries, I'll definitely have this video recorded and uploaded. And to just double check, yes, we are recording. So no worries, you can always come back. And one thing you can do is when you're watching, I should have said this earlier this semester, but let's just say it again. Anytime you're watching those videos, if you get to a spot where you're just not sure what I mean or what I said, or maybe if it just glitched out a little bit, you can always just say, hey, Mike, on that video on maybe it's the 10th of April on the timestamp of 32 minutes, 15 seconds. What did you say there? And I'm happy to take a look at that. I usually don't look at my videos very often, but I wouldn't be opposed to coming back to it. Well, other questions or comments so far? Okay, before we take a look at problem number 2, this one looks like a hypothesis test by the indication. Let's definitely make sure we hit this one, like we said, the one with the highlight mark. This is the one from the chi-squared procedure. And the way we can tell is, take a look at the data. We have, let's see, 7 categories, looks like the days of the week. And already, if you said categories, you're dealing with categorical data. There's 7 outcomes, so that means just by the form of the table, this absolutely looks like the chi-squared procedure. But let's double check by reading through the whole context. It says the report, Controlling Road Rage, a literature review and pilot study was prepared for AAA Foundation for the Traffic Safety by those folks. The authors discussed the results of a literature review and pilot study on how to prevent aggressive driving and road rage. Okay, so that's all good stuff. That sets the stage. It's the overall context, but there's no statistics we can deal with there. This is nice. They define road rage as an incident in which angry or impatient motorists or passenger, I didn't know about the passenger part, that's good information there, intentionally injures or, oh geez, kills another motorist, passenger, or pedestrian, or attempts to threaten or injure or kill another. This feels like some kind of legal statement. But we've got a working definition of road rage. You're just really upset and you want to hurt somebody. Seems like the takeaway there. I get it. Driving kind of sucks sometimes. They say next, one aspect of the study was to investigate road rage as a function of the day of the week. And that really makes sense. We had something similar. We were looking at homicides as they might relate to seasons, but there was no statistical significance there. It goes on to say the following table provides a frequency distribution on the days on which 69 road rage incidents occurred. Out of the gate, I don't know if it's random data, so we'll have to trust them that they got these data honestly. At least we have a sample size. N equals 69 incidents. Road rage incidents. And then, as this definition is indicated, people possibly got injured. Some of them might have died on these incidents. This is pretty serious data when you start looking at it. They asked us, does the data provide significant statistical evidence to conclude that road rage incidents are more likely to occur on some days than others? Well, just looking at the data, you might decide to yourself, I don't think we need to do statistics on this, right? There's clearly a problem on Friday, and we might have just known that just by how society operates. People are not necessarily very patient on a Friday. I would have thought that there's a higher count on Monday, though. I'm kind of surprised by these data. But Saturday being a big deal is just because people are out. People are a little bit more quiet on Sunday, maybe, just dreading going back to work on Monday potentially. But yeah, it looks like we have, in this particular problem, one variable. It's categorical. The categories are days of the week, which implies we have k equals 7 greater than 2 outcomes for this one categorical variable. So it's these two elements that we need to take a look at. The fact that we had one variable that was categorical, I guess 3 elements, and that the number of categories exceeded 2, or outcomes. So all this implies use chi-squared. Well, any questions, folks, on the method selection analysis for this one so far? Okay, I think once you start looking at these data tables, the way we see these data, sometimes it's just pattern recognition. This looks like chi-squared after a lot of experience because of the way it's just been formatted. So, oh, I didn't mean to do that though. It's Control-Z it. Let's now go through the complete analysis of this. For the state phase, let's see. If you find a question, again, you can always just cite it. I'm never opposed to that because all I want from here is you know what the thrust of the problem is. Usually this is not worth a lot of credit, but it's a good step because it directs what we're about to do, get your subconscious started on the problem. I would probably say here, is there a relationship between road rage incidents and day of the week? Looks like that's an absolute yes again by this huge jump we see in the data right here. If we were to plot this data table, we would see a big spike on Friday. If you'd like, you can plot these like we did on the first day of the course, in chapter 1. But I would say it's kind of up to you. I wouldn't say that's as necessary. The only plotting we usually do is more for condition checking. And checking conditions on chi-squared doesn't have anything to do with the plot of the data. So let's skip that unless folks would like to see it. Let me know. Feel free to interject at any point. So that's the state phase. In the planning phase, one thing that's a help with choosing chi-squared is it's always a hypothesis test. So if a problem asks you to use a confidence interval procedure, you're not using chi-squared. That would be a follow-up test after you found statistical significance. So we'll say here, because we're definitely using a hypothesis test, we need parameters and then we have to state our hypotheses. There are 7 outcomes, so we want to be efficient with this. We don't want to write out 7 sentences, that's tedious. So I'd probably go along these lines. Let P1, P2, P3, P4, P5, P6, and P7 denote the true, we could say probability, percent chance, anything along those lines. I'll go with probability. The true probability or you could say proportion. And you know what? I think proportion might flow a little bit better on this one. I'll go with denote the true proportion of, these are road rage incidents on 69 incidents, but it was probably from a specific area, maybe something like Bingham County, for example. It wasn't necessarily a national study, as far as we know from what we're reading. So I'll just say in a particular area when it comes to that. So the true proportion of a road rage incident on, this is the next tedious part, Monday, Tuesday, I'll just abbreviate these. Guess it's not that bad. Wednesday, Thursday, Friday. Oh, and I'm noticing I'm kind of making a mistake here. When you go to indicate these parameters, usually you want to keep a correspondence really, really tight so that we don't have any mistakes when we go to the further analysis. And if Sunday came first on the data table, I should have started with Sunday when I go to describe these, or else the meanings of these things are going to start to get foggy. So let me backtrack a little bit. Sorry to everyone working in Penn today. Let's start with Sunday, as our data does. So road rage incidents on Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. Now we get to say respectively, and there's our one-to-one correspondence. And I'll say here in this area, wherever it was. Okay, so we've got all of our hypotheses down. That's helpful. Next, we need a null hypothesis. And the null hypothesis is the statement that there is no relationship. Nothing interesting is happening at all. This just happened by chance alone. Well, if that's true, it's a statement that those true proportions we indicated are all equal. So we'll take these and just say the null hypothesis is that P1 is P2 equals P3 equals, no judgment if you decide to go ... and then end on P7. That's a pretty decent device for saving time. I'll write them all out though, just to make the notes more readable. Equals P4, P5, P6, P7. Now that we've listed them all out, it's a good idea to say what this probability is actually equal to, the common probability. Anyone happen to know the trick to get this value right here? And no worries if you're not sure, we've only studied this problem and finished the chapter Monday, so I totally understand. But the idea is all of these, whatever they had to add up to exactly one. That's what's happening in the null hypothesis. And if that's the case, it would be equal to 1/7. So that's pretty much what you would do in this kind of case. And if they had specific probabilities that every one of these was indicated as, it would have been stated somewhere in the problem. So without that further information, analyzing these data is just looking for any relationship. This is a statement of no relationship. Equal chance 1/7 of any one of those homicides in this area to fall on any day of the week. Doesn't look like that's going to be true for these data, so let's also indicate the alternative, but we have to anyways, so let's still do it. And for this one, I'll write it out to just using ordinary words. For chi-squared, sometimes that's not a bad approach. Let's say HA is the statement that at least one proportion is not equal to 1/7. Now, that's how the alternative hypothesis is typically stated, but for the folks who are very logically oriented, this could also have been said at least two, because if one is off, at least two are off logically. But you could write these out in any style that conveys the same meaning. Okay, we have a null, an alternative. The next thing I'm looking for is, was there a significance level? It just says provide a complete analysis. And on the real final exam, sometimes they'll say at a 1% significance level or 5%. Other times it's blank, and I'll just say in plan and choose your own level of significance. Here we get to do so ourselves, and I'll leave it up to any volunteer in the class. What would you say alpha should be? Awesome, I'll go with that. 0.05. Thanks for stating that one. I like this one because now it's a balance between a type 1 error and a type 2 error. So we have equal balance in both directions that way. Finally, after that, we get to the solve phase. For chi-squared, there are two steps. Now, sometimes some of these problems are going to involve just summary data. Like I think this problem right here is simply summary data. I won't ask you to check the conditions on those because, I mean, actually, this one isn't summary data. I thought it was quantitative. If all you have is X bar and S's, then we can't really do this step unless it's chi-squared. We can do this one thing. Here we'll check conditions. We do not know at all if these data were random. We're just going to trust them on that. But what we can check is if all the expected outcomes are larger than 5, we're all set. If one of them is less than 5, we're still okay. We just do not want more than 20% of these observations to exceed, or excuse me, to be below 5. If a single one of them equals exactly 1, then the whole procedure is over. The conditions are not met. So let's grab this table. And start with this value right here. That 1/7 is considered a P naught. And we need that because now we check conditions by doing the following. The expected counts, and my table here is not going to look too great. So let me try and fix that. The expected counts will go like this. We need an expected count for every day of the week, but it's not as bad as it sounds because the way we calculate is we take the sample size and was, I forget, let me double check to be sure, 69 incidents. We take the sample size and for the probability of P1, we just take that multiplied by 69, and that's going to be the expected count per Sunday. But on this problem, all of the parameters are equal, so you're really just going to take n times P naught one single time, and that gives you every single expected counts. That's always kind of a nice feature of these sort of problems. So let's take a look. Our sample size is 69. We multiply it by P naught, and P naught is 1/7. We can just say divide by 7 to shorten that up. And so every expected count comes out to about 9.9. That's good. That means the conditions are met. Nothing is below 5. It's a little bit tedious to write these all out, so let me finish out the table. 9.9. Let me know if I forget the day of the week. That's easy to do at this point in the semester. This looked like a fun problem, but it's also a bit tedious with all these outcomes, but we finally have it. These are all the expected counts. What we mean by that is, if the null hypothesis were really true, and we do the study over and over and over again at the same sample sizes, then average all the data that you actually get, like this time, these are the observed counts, and on average, they should look like this. But there is a big difference between every single expected count you see here, notably from Friday as well. A lot of these are just way, way off. So it looks like we are in fact going to reject the null hypothesis. We still have to get a p-value to finish off the procedure. And the way you calculate that is entirely up to you. Let me see if I remember how to delete a table. There it is. You can make RStudio do all of the heavy lifting for you. You could do it by hand, completely up to you. We've tried both methods. On an exam like this one, I'd probably just do the following. Take a look at the original data up there. I'll save the syntax for this in case you'd like to copy that approach, this approach. First thing we want to do is just import the counts. We need the expected counts, and they go 5, 5, 11, 12, 11, 18, 7. Just double checking we've all got it. Then next thing you want to take a look at is your null hypothesis. If you have specific values, like we did on the last question in chapter 21, then you need a new vector of probabilities, and you have to import it or state it inside the chi-squared function. But if they are all equal, actually all you need to do is go chi-square.test, give it counts, and that's the entire syntax for this procedure. Let's see if it actually works. So Control-A, Control-Enter gives us, yep, that's exactly what we wanted. Let me first copy in the syntax because I have a penchant for forgetting to do that a lot. Okay, so that's back in. Now let's also grab the output right here. And I think I did forget part of what I was doing. We had really good expected counts, but I should tie off this statement and say we jumped to the solve phase. I should say up here, the sample size is large enough. And so the conditions are met. Possibly, we still have that massive requirement that the statistics was really done correctly. The more you learn about statistics, the more you start to see that this side of actually gathering the data is really, really involved. And if this goes wrong, it's heartbreaking because your entire work could just be rejected by the peer-reviewed journal if we didn't get the data right. So I'll also say down below here, the conditions are met, provided these data came from a random sample. Okay, so we've got our conditions down. Then I kind of combined steps there. Sorry about that. I think I'm just trying to make sure we get to a lot of problems. The solve phase gave us a rather large chi-square test statistic. Our p-value is at 0.04, and that's amazing. This one was chosen at just the right amount to lead to a rejection. You know, I would have thought the p-value is much more smaller, but that's why it's so important to actually do this appropriately. A big blip right there is very, very deceiving. It wasn't as statistically significant as we might have thought. If someone chose 0.01, we would have given a different conclusion. But hey, we just barely made it. Let's say that this one is less than 0.05, which was the significance level alpha specified. So last thing to do is just give a conclusion. And again, these kinds of conclusions with hypothesis testing are almost always unsatisfying. It's kind of weird. But when you study more statistics, you'll realize the chi-squared procedure that we just used is the overall test looking for any difference. And when you reject this, you could do even more statistics to look into the nature of the difference. We would look into chi-squared components. If we said it was due to Friday, we could start giving confidence intervals throughout the data and so on. It's as if these things just keep going and going and going. So if you like statistics, you can have an endless time learning more about it. But here's our not so satisfying conclusion, but it's an honest one. We have found statistically significant evidence of, we have to be really careful here. I want to say a relationship between days of the week and road rage. The thing that we have to be really careful on this conclusion is that statement there. It's not a very strong statement. We would rather say something along the lines of Friday or cause of road rage, or it's the days of the week that cause road rage. But we cannot give a cause and effect conclusion at all for these kinds of data unless there was some kind of controlled designed experiment. I don't even know how it would work in this kind of context. That it wasn't an experimental design, they were just grabbing incidents of road rage and looking at what happened with the data. Looks like there is a relationship going on, but not as stark as we might have thought. Well, any last questions, folks, on getting through this one? Okay, so that's how chi-squared goes. When you get to here and you find statistical significance, if you want to look into this further, what you want to look into is the chi-squared statistic and find out which term or which component was the largest to contribute to the size of this. Probably Friday is the largest one on there. And then that's how you start to do follow-up tests to analyze the nature of the relationship that we found exists in these data. But at the moment, we're done with this problem. So let's go back up to the top here. And this is our next one for the day. Any questions before we take on this problem here, folks? Okay, looking at this problem, let's see. It says, a recent study compared 298 children with the autism spectrum disorder, ASD, to 1,507 randomly selected. Already that's kind of interesting, right? They said randomly selected control children without the order. They didn't say how they got the 298 children with the autism spectrum disorder, so that's a little bit interesting on their design. We hope that that's a random sample as well. It goes on to say, of the children with autism, 20 of the mothers had used antidepressant drugs during the year before pregnancy or the first trimester of pregnancy. So that's interesting. Of the control children, 50 of the mothers had used the drugs. So that's kind of a weird statement there. And they go on to ask, is there a statistically significant association? Again, they're not even trying to ask about cause and effect, and they can't. This would have to be a designed and controlled experiment. And you cannot assign people to ASD and not ASD. That's impossible, right? So there's no way to get cause and effect on these data. But they want to look for an association between prenatal exposure to antidepressant medicine and the risk of autism. This is, in my opinion, a pretty silly question, but it's something that happens in statistics a lot. You might find a question that just gives you a knee-jerk reaction. In class, I try to just be as neutral as possible to the best of my ability. But if I'm honest with you, I think this question is just completely silly. Yet, if it's posed to you and you're the statistician in charge, we still have to treat the data with respect, even if it still seems like this is a really weird question that we're taking a look into. I haven't actually analyzed these data, so we'll see what goes on with it. First of all, before we do anything with this, there are two populations, right? Or two independent populations. There is the 298 children with ASD. So let's say N1 is 298. There was 1,507 children without the disorder. Let's call that sample 2. And 2 is Y1507. And next it says, of the children with autism, 20 of the mothers had used antidepressant drugs during the year before pregnancy or the first trimester of the pregnancy. We'll probably paraphrase that statement. People are always looking for some weird association for autism, but it is an extremely nuanced problem. So although people are looking, and this is probably not going to give a significance, I don't quite know yet, I would say it's still important to treat even a silly question like this one with at least the respect it deserves, the data itself. So 20 mothers had used antidepressant drugs. It sounds like that's the success in this problem, the thing that we're interested in, prenatal exposure. So let's say here, X1 is 20 successes. Now let's highlight this right here, had used those drugs. We're not quite sure which ones, but that's our success. And next, of the control children, it's kind of a weird way to say that, but the children without the disorder, 50 of the mothers had used the drugs. So X2 is 50. Successes. And now that we've listed all this out, and the fact that we said successes means there's a categorical variable. Its outcomes are going to be success, prenatal exposure, and failure, no prenatal exposure. So one categorical variable is use of antidepressant drugs, and there is exactly 2 outcomes. So the next variable is, well, we have 2 populations. So the next categorical variable is describing which of the individuals in the study go to this population and go to this population. So there is another categorical variable with exactly 2 outcomes. Now, interesting about this is if you have two categorical variables, both with at least 2 outcomes, you can actually use chi-squared on this, but it would be a chi-squared procedure for 2-way tables. Much more easily is we're going to use the 2 sample Z methods for proportions. So that will be the actual method that we use. This one was in chapter 20. What causes us to use the method? The fact that we have 2 variables with exactly 2 outcomes allows us to use this method in chapter 20. So we're all set. We have sample sizes. We have a notion of success. It says perform a complete analysis with a hypothesis test. So we'll just go on down the lines. So first, state. We want to know, is there a relationship between antidepressant drug use, and I'll just say that paraphrase statement, and autism spectrum disorder? Is there a relationship between, I'll paraphrase autism spectrum disorder to ASD, and how we say that prenatal exposure to antidepressants. So that's our question to analyze. It's going to be a hypothesis test. So, well, whether it's a hypothesis test or not, we have to define both our parameters. And there's going to be a P1, P2. They're both estimated by P hat 1. P hat 1 is just going to be 298. Or let me try again. Let me flip that. It's going to be the 20 successes divided by the sample size, 298. So that estimates the first parameter, P1. Estimated for P2 is going to be P hat 2, coming from these data. The sample proportion of successes would be the 50 successes divided by the 1,507 children in this group. And so let's say let P1 and P2 denote the true proportion of, it's always the true proportion of successes specifically, but we have to say what that is in context. So we were kind of work backwards. If we said we had 20 successes here, we'd come up to the data. And where did the 20 come from? It was the mothers that had used the antidepressant drugs. And so we can say the true proportion of mothers that used antidepressants. And there's a lot more statement here, but we can leave this bit in context. We mean during the year before pregnancy or the first trimester, which led to the prenatal exposure. We don't have to necessarily say all that. And if it feels like you're copying the whole problem down or half of it, then you always are welcome to be a little bit more terse. Make sure you get the major elements of what we're studying. The fact that the successes were the mothers that used the antidepressants in this problem. So we'll say true proportion of mothers that used antidepressants. Well, there's also two populations. P1 is referring to this group, which is the autism spectrum disorder children. So we'll say for children with ASD and for children without ASD, respectively. Okay, we've got our parameters in. So it's a hypothesis test. So next thing we have to do is state a null and alternative. Let's also take the problem down with us as we go, just so we can be careful with the context. If it's a hypothesis test, there's lots of things to decide on, like is it a right tail test or left tail test and so on. So let's start by saying we will test a null, and this is pretty similar to chi-squared. In fact, we just mentioned you could analyze this data with the chi-squared for two tables method. The null hypothesis is a statement that there's nothing going on in the population, and that would be a statement that P1 equals P2. Or you might say P1 minus P2 is 0. That's an equally appropriate way to go. So we'll test that against the alternative hypothesis, HA. So in the alternative hypothesis, let's take another look. The question was, is there a statistically significant association between prenatal exposure to the antidepressant medicine and the risk of autism? They asked for an association, but they didn't say a direction. We're not saying it caused an increase or a decrease. So this would be a two-tailed test. P1 not equal to P2. And for this problem, I'll select the significance level alpha on this one. I think this problem is very interesting to me. And what I would never want to have happen for this kind of study is that it gets done 100 times because 5 of them are going to reject the null hypothesis when it's in fact true. That's just the nature of the significance level alpha. So this is a context where I would probably want something more like this. Let's go for a really, really high bar. And I think it's appropriate because a humongous claim like this one deserves a high bar for evidence as well. So if you feel like you have a strong reaction to a problem in the ones on the final exam or your homework questions, That's a pretty appropriate thing to do as well. So let's see if we can pass that bar, but in doing that, we now need to run through the rest of the process. We need to take another look at the data, see if our conditions are met. We should be all set here because if we're running a hypothesis test, all we need is 5 successes, 5 failures in both of the samples. But these things are really, really tricky. When you're looking at chapter 19 and chapter 20, it almost feels like there's 4 different methods there because of how different condition checking is. So what I would encourage you is the moment you know you're in chapter 20, go to the Moodle website immediately, go to that chapter. I'll grab this one, the summary document, and just double check. Number of successes and failures in both samples, at least 5. That's where we should be looking because we're doing the hypothesis test. If it was confidence intervals, we're doing the successes and failures in the sample, at least 10. And if it's chapter 19, this is entirely different. You're doing it more like chi-squared, looking at expected successes, expected failures. So back to this problem. On the solve phase, we're now just checking conditions. On the first step, we can say well, let's maybe organize this a little bit better. We have 2 samples, and we have to give successes and failures in both samples. So let's say for this problem, this will be the ASD group, and this will be the not ASD group. In this group, we have 20 successes. And I did want to put a statement right above that. It's not a bad idea to put in the benchmark we had to hit, greater than or equal to 5 successes. And how many failures? Just take your sample size, 298, subtract the successes, so it's 278. Definitely exceeded that, greater than or equal to 5 failures. Then that means we're all set on this group. For the other population, the sample size is even larger, so this is just a formality. We do have to write these down on the real exam, but that's just more me knowing that you looked at the right benchmark for successes and failures. So I'll say here there are 50, which is definitely greater or equal to 5 successes here. And we'll have 1, 4, 5, 7, greater than or equal to, let me fix my penmanship first, greater than or equal to 5 failures. This shows that the sample sizes are large enough. So we'll say here, the sample sizes are large enough. Now it's almost kind of heartbreaking. It looked like we had random data because they told us that this group, 1507, were randomly selected children, but they gave no such information for the children with autism spectrum disorder. So at that stage, it's just a completely unknown. I'll say here, the conditions are met, provided the sample of ASD children were randomly selected. Okay, so that's the ending of the solve phase. We're just about there. Now we're on the mathy portion where we now have to calculate a certain statistic. Take a look at the standard error, or excuse me, not the standard error, the standard error of that statistic, then a test statistic, and then a p-value. So still a lot of hoops to jump through. Any questions at all, though, with the condition checking? Okay, so it's a little bit weird in chapter 20 is if you're testing a hypothesis like this one, P1 equals P2, very first step is you assume that's true. That means there is no differences in the population, and both samples are estimating a common estimator. So we'll say, let P hat equal the pooled sample proportion of successes. So that's a random statistic out of nowhere. It only appeared in chapter 20, and it only appears in the context of hypothesis testing. So we say p hat equals x1 plus x2, divide by n1 plus n2. x1 and x2 are the successes, so that's what we mean by pooling them together. We'll have 20 plus 50 divided by 298 plus 1507. I'll leave this in fraction form to get more accurate answers. So this is 70 over 1805. So once we have p hat, the next weird standard error is this one. This formula only appears in chapter 20, and it only appears in the context of hypothesis testing. Chapter 20 is kind of a weird chapter for this kind of stuff. The formula went p hat times 1 minus p hat multiplied by 1 over n1 plus 1 over n2. So let's fill in the information on this one. We'll have square root of 70, 1805 multiplied by 1 minus 70, 1805, multiplying reciprocal the sample sizes. So we should look down over here to get those values. 1 over 298 plus 1 over 1507. Never seem to make those square root bars long enough. So that will give us our standard error. And we're just about there. Well, we need a test statistic next, but we're getting there. So another calculator operation. Square root of 70, 1805 times 1 minus 70, 1805 times 1 over 298 plus 1 over 1507 gives us that as a standard error. Let's see, let's go for maybe 0.01224. Let me just double check the digits. Okay, I think we've got a standard error. Does that look right to folks so far? Okay, after you get this quantity, we're now ready for the test statistic. This is going to be a z-test statistic, and that's a good thing to write it as either z or t, because it reminds you where you're going to get your p-value. Because we call this formula z equals, we're using the normal distribution for p-values, and it's defined in this way. We return to the original statistics, p hat 1 minus p hat 2. We divide by the standard error we just calculated. And now we have 20 over 298 minus 50 over 1507 divide by 0.01224. And this is kind of exciting. We're going to see if we have significance here or not. I mean, we still need the p-value, but if z is 0.2, we're going to fail to reject the null hypothesis for sure. So we get a good idea just from this one step. So let's take a look. It'll be 20 298 minus 50, 1507 divided by 0.01224. And wow, that's a lot bigger than I thought. This came out at 2.772. I was assuming this is going to come out pretty tiny, but that's nearly 3 standard deviations. So this could potentially actually be significant. Next step we need is a p-value. And for the p-value, we're just going to use, let's see here, it is a two-tailed test. So let's remind ourselves of that first by taking another look at our hypotheses. Because of the not equals there, we'll go for a two-tailed test on this one. And that means the formula should go like this. 2 times p norm, grab it this value, 2.772, and then put in lower dot tail equals false. So next, back up here, 2 times p norm, just copying the syntax we have right here, 2.772 lower dot tail set false. And here's our p-value. It's at 0.005. Holy crap, that is just barely bigger than this one I indicate right here. And I don't know if you believe me, but this was my first time looking at these data. I was debating making it a 0.001, but I felt that that was kind of extreme. And now we are just at the cusp here, 0.0055. But I still feel like this was an appropriate significance level, in my opinion, since there is, again, if this null hypothesis is true, and we said 0.05, there's a 5% chance that we're going to reject this when it's actually a true statement. And that is a humongous statement that's being made right there. So I'm kind of glad that we have a slightly bigger actual significance level alpha. We'll say here that this is bigger than 0.05, which is equal to alpha, just by a smidge. So we will fail to reject H naught, which means we still return to the alternative hypothesis statement. But what we're going to say is we don't have enough evidence. We wanted a lot, and I think that's appropriate for this kind of problem in order to conclude that that was really true. So let's go on and say these data do not provide significant statistical evidence. I would probably want to be upfront though on this problem. I used a and I made a mistake here. I used a very punishing level of significance, 0.005. So let's say that as well. At the 0.005 significance level, that this is true, that the proportions are different. Now we have to say what those proportions were once more. They're the true proportions of mothers that use antidepressants for children with ASD and for children without ASD. So we don't have significant evidence that the proportions of mothers of children with ASD that use antidepressants is different from that proportion of mothers of children, my hand is actually getting tired at this point, we're almost there, of children without ASD. So that's the end statement on that one. Any questions, folks, on analyzing this problem here? Okay, definitely kind of exciting. It's always weird doing a problem when you have no idea how it's going to go out. And I was kind of shocked. I was almost certain when I read through the problem that that was going to be a low value, but it was very close to significance at a punishing level of significance as well. Interesting problem. But keep in mind, these are random data and weird things like this can happen. Even when the null hypothesis is absolutely true, you stand a chance to reject it just by repeating the study over and over again. This would have 5 times out of 1,000 that we would reject the null hypothesis when it is indeed false. That's one of the reasons that we have such a need for replication in the sciences. One significant result alone doesn't mean a whole lot. But if you do the same problem and you get 3 different p-values, you can now do a meta-analysis. P-values can now combine to a larger overall p-value, and we get better insights into the problem the more and more these kinds of studies are replicated. But that's where this one ends right here. The next one is on snake trail leading chemical deposits. We won't get to this one in time, I think. I think this is a good stopping point for us. But any last questions at all, folks, whatsoever? Okay, I will come back to these problems, like I indicated, after grading assignment number 10. So if you're working on the final exam and you just want some inspiration on how some problems might go, come back to here, it will get updated. But now it's the time we can do the most exciting thing in the course. We're about ready to end it for the day. And this is the final exam. It's set up like an actual homework assignment. So when you click on this, it has a due date. The due date is May 1st, a week away from today. I have two problems that have data files, so problems 4, problem 6. And just like the homework assignments, there's a Word document. If that works well for your machine, sometimes people do not like these. It could be some incompatibilities, or PDF for just extra compatibility. So here's what it looks like. Same kind of statement on exam 2, since it's a take-home exam. It's essentially open everything except other humans. So you can use anything except a human source. But you're welcome to use other materials, say other textbooks, places online that you used to study. Those are completely fine. Just be sure to cite those sources if you go outside the course content. But aside from that, I did do the randomization as mentioned, and I only hit the randomization button once, so I'm not trying to cherry pick anything. Here's what all the problems look like. Some of them are kind of silly, but it makes them entertaining to run through. Here we're trying to decide if people can tell the difference between pate and dog food. So that's an exciting experience, I think. Other problems are just weird data tables where we're going to have to try to figure out what is the right kind of procedure for this. And some other problems are kind of open-ended. This one just says use a confidence interval. So we would not state the null or an alternative hypothesis on this one. There is none. But you do have to choose a confidence level on this. Some folks might go 90%, 99%. It's all up to you. And if you're just not sure, if you feel like there's just nothing exciting about social media jeopardizing your job, 95% is a pretty standard middle of the road kind of confidence. Other problems are big, like this one right here. It's not as big as it looks. I just collapsed the table, so I didn't take up the whole page showing the data. And that's where you're going to find data files. Oh, I didn't download that, but that's where the data files, problem 4, problem 6 come up. And scrolling through this, I don't know if I have too much more to say. Let's see here. This is just another problem. Looks like acrylic bones cement, so we're looking at some kind of reliability on those things. This will be a fun one on subliminal messages. And I do feel like I want to give one hint on this. Mainly because when we did our review problems, we analyzed our variable in this very first problem. This analysis does work, but we have to pick a way to decide these analyses. I put on our review document, look at in these kinds of terms to choose the right method. So because of this mistake right here, let's throw out one hint on the final exam. This problem right here is the 2-sample T procedure. So that's our big hint on the final. It's 2 independent populations, and we're going to determine if a subliminal message of each day I'm getting better at math, or if you're signing into Zoom, math is fun, that's my subliminal message. If that had any real impact, that'll be kind of exciting. Well, that's the whole exam. Any questions or comments whatsoever, folks? Okay, well, have a great night. If questions come up, especially RStudio questions, please don't hesitate to reach out. I'll be very happy to help out. Otherwise, have a great summer, folks, and I'll see you all later, potentially.